Alright, welcome back. Math 1910. We're in Chapter 3, Section 3. We're going to talk about increasing and decreasing functions and how we can use the first derivative to determine if a function is either increasing or decreasing on an interval. Okay? And then using the first derivative test to actually find out if that function has a relative extrema on that interval as well. Okay? So let's first define what increasing and decreasing are. So, I mean, these are fairly common sense, nothing real new here. All right, just basic algebra. A function f is increasing on an interval for any two numbers x1 and x2 in the interval. All right, if x1 is less than x2. All right, so that implies that f of x1 is less than f of x2. So that defines an increasing function for us. Alright, and then we have if a function is decreasing on an interval when for any two numbers x1 and x2 in the interval, alright, x1 is less than x2 implies that f of x1 is greater than f of x2. That function is decreasing. So think about as we're moving left to right, alright, x1 on the left, x2 on the right. So as long as x1, okay, is less than x2, alright, and f of x1 is less than f of x2, right, we're increasing, and then the opposite for the decreasing piece. All right, so graphically, let's take a look at this approach here. We can clearly see that as this function is moving from left to right, all right, y is decreasing from the interval negative infinity to a, then it's constant from a to b, and then it's increasing from b to infinity. So we should be able to look at this graph and understand what it means, like increasing, decreasing functions. You guys learned this in like 7th grade math, 8th grade math, somewhere around in there. Okay, so how do we know this? All right, we're going to go through the derivative test. So to know if a function's decreasing, its derivative is going to be less than 0. If its derivative is 0, it's constant, and if its derivative is greater than 0, it's going to be increasing. So there's how we can kind of use the derivative to understand this. So how do we write that out? We take a look at Theorem 3.5. That's how we test to see if a function is increasing or decreasing. So let f be a function that's continuous on a closed interval a to b and differentiable on the open interval a to b. So we can define these three different definitions here. Okay? If f prime of x, if the derivative is greater than 0 for all x in a, b, then f is increasing on the closed interval a to b. So as long as the derivative, whatever you get out, is greater than 0, that function, the original function, is going to be increasing. So this is how we're going to use the derivative and relate it back to the original function. So if our derivative is less than 0, indicating that our derivative value is negative on that interval a to b, then f is going to be decreasing. The original function is going to be decreasing on that closed interval a to b. And then lastly, if we have f prime of x, our derivative, if it's equal to 0 for that interval, that means that the function is constant. It's not increasing or decreasing on that interval a to b. So those are the three tests that we're going to go through as we apply Theorem 3.5 to work and look at and understand if a function is increasing on an interval, decreasing on an interval, or remaining constant on an interval. So let's take a look at this function here. We want to find the open interval on which this function, x cubed minus 3/2 x squared, is increasing or decreasing. All right, so it's important that we find those, those specific values, critical numbers, things like that. All right, so our first piece is we should know this function is differentiable on the entire number line. So we're going to take the original function and write the derivative of it. So the derivative, f prime of x, is 3x squared minus 3x. All right, so once we have the derivative, okay, we're going to take the derivative and set it equal to 0. Okay, we're going to take the derivative, set it equal to 0, solve for x. So this is one where we're going to factor out a 3x. Okay, so we're going to be left with 3x times the quantity of x minus 1. We set each term equal to 0, right? So 3x equals 0 and x minus 1 equals 0. So that tells us that x is either 0 or x is 1. So those are our critical numbers, and we've done that in previous lectures, so we understand everything that we're doing here so far. This is nothing new, but we're going to evaluate and test points. using the derivative. So we know that 0 and 1 are critical numbers. Those are later on in what we've done in the previous chapter of actually, finding where the max or the min could occur, the extrema, right? But we're going to use this as test points. So remember, here the critical numbers is when the derivative is equal to 0, and we're going to test. We're going to test values to the left of 0. We're going to test values between 0 and 1, and we're going to test values that are greater than 1. So when we test those, we're going to look at those different intervals, and based on those intervals, we're going to be able to tell if a function is either increasing or decreasing or constant on that interval. Okay? So let's take a look. So you're going to create yourself kind of a chart like this one. So if we look, remember our critical numbers are 0 and 1. Okay? So we have to choose test values that are easy. Remember, our first test value has to be between negative infinity and 0. God. So a good, easy, always choose values like 0, 1, a half, or things like that that fit nicely in our intervals. So our interval here is from negative infinity to 0. We have to check the values less than 0 because 0 is one of the critical values. So we are going to arbitrarily choose a test value of negative 1. So what we need to do is we're going to substitute the value of negative 1 into the derivative. When we do that, we get f prime of negative 1. We get a value of 6. 6 is greater than 0, right? That tells us it's positive. So we can conclude on that interval from negative infinity to 0 that our function is increasing. All right, let's look at the next test interval. Remember, the critical values are 0 and 1. So we need to choose something now between 0 and 1. So we're going to arbitrarily pick x equals 1/2. It's dead center, right? Between 0 and 1. So what we're going to do, we're going to substitute 1/2 into the derivative. So when we do that, we take f prime of 1/2 and we get negative 3/4. That value is less than 0, right? Because it's negative. So that tells us, since that function is negative, on the interval from 0 to 1, this function is decreasing. The original function will be decreasing, not the derivative. Okay, so it's important for us to look at that aspect. Last interval, remembering that our critical numbers are 0 and 1, our last interval has to occur after the value of 1. So we're looking at the interval from 1 to infinity. So we're going to pick 2, all right? It's after 1, and it's in the interval 1 to infinity. Don't pick difficult values to work with. All right, so we substitute 2 into the derivative. So we take f prime of 2, and we get a value of 6. 6 is greater than 0. It's positive, which tells us the original function is increasing there. So when we do that, all right, we can use all 3 different intervals now to conclude when a function is increasing or decreasing. On our critical numbers, 0 and 1, we chose 3 different test intervals. If you have 3 critical numbers, you have to choose 4 test intervals. Okay, so it's just going to vary on what your critical numbers are. Remember, we calculate the critical numbers when the derivative is equal to 0. So we can now conclude, based on our test values, we're using the derivative to conclude what's happening to the original function. So the original function here is going to be increasing from negative infinity to 0. It's going to be decreasing from 0 to 1. And it's going to be increasing from 1 to infinity. All right, so if we take a look at this graph here, this is a graph of that function. Remember, the original function is x cubed minus 3/2 x squared. So we can conclude the intervals of which it's increasing or decreasing based on what's happening to the derivative. If the derivative is negative, all right, we're decreasing. If the derivative is positive, we're increasing. And if the derivative is equal to 0 on those intervals, then our original function is constant. All right, so we can see how the graph works. We're going increasing, decreasing, increasing. All right, so these are just some guidelines that you might want to follow. So I would write these down as you're doing your homework, or have this slide up, as you do it. So step 1, right, find the critical numbers. So take the derivative, set it equal to 0, those critical numbers, okay, and use those critical numbers to determine your test points in your intervals. The critical numbers will help define the intervals, and then in between those intervals is where you choose your test points, okay? Then we do step 2, determine the sign of the derivative of x at your test values, okay? In the intervals. So determine the sign of the derivative of x. All right, determine if it's negative, positive, or constant, all right, or 0 there, so we know that it's constant. All right, and then based on those conclusions, all right, you use theorem 3.5 to determine whether the function's increasing, decreasing, or constant on the interval. All right. All right, so let's talk about what's a strictly monotonic function. Okay, a monotonic, mono means it's doing the same thing the entire time. That's really all a monotonic function is. So if we take a look at this function here, f of x cubed, it is increasing from negative infinity to positive infinity. So regardless of what the intervals are, right? We might have a critical value at 0, but on the left-hand side of that, we're increasing. On the right-hand side of that, are increasing. So this function is called strictly monotonic. It is always increasing. A function could always be decreasing as well, and it would still be monotonic. It means it's doing the same thing across all of its intervals. So for all time. So negative x cubed, all right, would be constantly decreasing or strictly monotonic as well. Functions that look like this, though, all right, where there's actually a spot where they have a constant value, these are not monotonic functions, because even though it looks like they're constantly increasing, all right, there's a specific point here from 0 to 1. There's an interval where they are a constant value. Since that means that they're not increasing there, this is not a monotonic function. Okay, so what did we really do, though? We used the first derivative test. We did this in the last lecture, when we can use that to find the relative minimum or the relative maximum. Because remember, that occurs at the critical values. And this is where, it's important to understand the increasing to decreasing to increasing piece as we look at this. So remember, we calculated, this is still the same function we did before. We calculated the critical values. They were 0 and 1. All right, and then we did our test intervals, and then we concluded, all right, the function's increasing from negative infinity to 0, it's decreasing from 0 to 1, and from 1 to infinity, it's increasing. Well, that helps us conclude whether we have a relative minimum or a relative maximum here. So when our derivative here, okay, our derivative goes from increasing to decreasing, so at 0, we have a relative maximum, right? It's increasing and then it starts decreasing. That gives us a relative maximum, all right? And then our derivative, okay, on the interval from 0 to 1, it was decreasing, and then from 1 to infinity, it was increasing. So since we went from decreasing to increasing, our function has a relative minimum at the critical value. So the critical points are really important, okay? They not only tell us, what intervals that our function is increasing or decreasing on, it also tells us if we have relative maximums or relative minimums that occur at those critical values here. All right, so very, very important when we do that first derivative test. All right, so here's what it tells us. Okay, and it's kind of what I just walked through with you, but if we have theorem 3.6, okay, so if you understand, what we're talking about here, if f prime of x changes from negative to positive at c is our critical value. So if we're going from negative to positive, which means we're going decreasing to increasing. That's how I want you to understand that. We're going from decreasing to increasing. So that's what negative to positive means, because we are analyzing the derivative, not the original function. But what's happening at the derivative tells us what's going on with the original function. So if f prime of x changes from negative to positive at c, our critical value, then the original function has a relative minimum. Okay, we're creating that value. Point 2. All right, if the derivative changes from positive to negative, which means we're going from increasing to decreasing, we get a relative maximum at that critical value. Then the third point, if the derivative is positive on both sides of the critical value, or if the derivative is negative on both sides of the critical value, there is neither a minimum nor a maximum value on that point. Okay, so if the derivative is constant, all right, and the sign doesn't change, okay, on the derivative, we will have no maximum or minimum there. All right, so let's do an example here. We want to find the relative extrema of the function f of x equals 1/2 x minus sine of x on the interval from 0 to 2 pi. We know this function is continuous on the interval from 0 to 2 pi. So the first thing we should do, let's find the derivative. The derivative of this function is 1/2 minus cosine of x. Okay? Now, we have to find the critical values, so we're going to take 1/2 minus cosine of x and set that equal to 0, and we need to find when cosine of x is equal to 1/2. After you do that, so we're going to take 1/2 minus cosine is equal to 0, the derivative equals to 0, and then what that tells us, when is cosine equal to 1/2? Well, cosine equals 1/2 at pi over 3 and 5 pi over 3. So those are our two critical numbers. So now we set out our table, and we're going to pick our intervals, and we're going to do our test points, and then we're going to be able to conclude everything we need to know about the original function when we do this. Okay, so the critical values, pi over 3, 5 pi over 3. So when we do this, all right, our first interval is going to be 0 to pi over 3. Our second interval will be pi over 3 to 5 pi over 3. And our last interval will be 5 pi over 3 to 2 pi. Okay, so since we have two critical values, we have to have three different intervals. So if we're looking at the first interval, 0 to pi over 3, right, we're going to pick a test point that's between those. Okay, so remember, pi over 3 is 60 degrees for you guys. So remember, what's between there that's a good one is pi over 4, because that's 45 degrees. So if you still are lost with the pi over 3, pi over 4, that sort of thing, I'll put them back into degrees so that you can choose, okay? And then, so our test value is going to be pi over 4. So remember, we substitute our test value back into the derivative. All right, so when we do f prime of pi over 4, okay, that gives us a negative value, f prime of pi over 4. When we substitute the derivative in, it ends up being less than 0, so we can conclude on that interval the original function is decreasing. All right, let's do the second test interval, pi over 3 to 5 pi over 3. Let's arbitrarily pick pi. It's a good value to use as our test value that's in that interval. Okay, so we're going to choose pi. So when we do this and substitute pi into the derivative, okay, f prime of pi ends up being positive. It's greater than 0. So that tells us the function is increasing on the interval from pi over 3 to 5 pi over 3. Okay, and then we have the last interval, 5 pi over 3 to 2 pi. Something good for us to pick between there is 7 pi over 4. We substitute in 7 pi over 4. So f into the derivative. So f prime of 7 pi over 4 is negative. So it's less than 0. That tells us the function is decreasing. So now we can conclude on the interval from 0 to pi over 3 that the function is decreasing. From pi over 3 to 5 pi over 3, our function, the original function, all right, is increasing. And from 5 pi over 3 to 2 pi, all right, the original function is decreasing. That also tells us where our extrema is. So if we are still looking at this chart here, if our function went from decreasing to increasing, so at that critical value of pi over 3, this function has a minimum, okay? Then on the next part, we go from the middle interval to the interval on the right. Our function goes from increasing to decreasing. When we go from increasing to decreasing, okay, we have a maximum there. So 5 pi over 3, there's a maximum at that critical value. So now we know that there's a minimum at pi over 3 and a maximum at 5 pi over 3. And it helps us, to analyze the graph here. So we can see where that's happening. So we used the first derivative test to learn a lot of things about this function. We learned when the function was increasing, when the function was decreasing. And based on the function and when it changed from increasing to decreasing at the critical values, we were able to tell we went from decreasing to increasing first, right? So we had a minimum, so that's where our relative minimum occurs at pi over 3. And then it went from increasing to decreasing at 5 pi over 3, so we knew we had a relative maximum. If you need to find that value, you would substitute pi over 3 into the original function to get the y value, and you would substitute 5 pi over 3 into the original function to get the y value. Alright, so hopefully you guys now understand how we can use the first derivative to test to see if a function is increasing or decreasing, and to see where its relative minimum and where its relative maximum could be, alright, based on the critical numbers. Alright guys, that's the end of this lecture. If you have any questions, feel free to email me. Let me know if we need to Zoom meet, team meet, or anything like that. Else guys, I will see you in class. Have a great day.